And the next speaker is Alexander Lev from MIT. An important detail about him is that he will be on the academic job market next year. And he will be presenting probabilistic programming with stochastic probabilities.
Great. Thank you for the introduction, and hi everyone. My name is Alex Lev, and I'll be talking about some joint work with Matt Ghavami, Martin Rinard, and Vikash Mansinghka. So probabilistic programming systems are an emerging class of tools for building software that can solve probabilistic reasoning tasks. They've been applied to create systems that do everything from perceiving cluttered 3D scenes to interpreting and predicting economic trends more accurately than leading industry solutions like Facebook Neural Profit. And probabilistic programming systems enable these applications with two key technical innovations. First, they feature modeling languages that let users express probabilistic models as programs, making it easy to write down probability distributions that are defined in terms of expressive, program-like components. The probabilistic models behind these example applications are defined in terms of 3D renderers, symbolic planners, scientific simulators, and so on. The second thing that probabilistic programming systems do is to automate mathematical operations on these models. This automation makes it possible for users to concisely implement sophisticated algorithms for probabilistic reasoning, such as the variety of Monte Carlo and variational inference algorithms that power these example applications. Now, how can this broad class of algorithms be supported by the same tooling? Well, I'm showing here 3 examples of different inference algorithms for probabilistic reasoning, and although they're all different, they rely on the same core operations: simulating from probability distributions and evaluating probability densities. Or more often, you're evaluating probability density ratios, which quantify how much more likely an outcome is under one distribution than another. And when we design a probabilistic programming language, our goal is to craft a modeling language that's really expressive, but also that makes it possible to efficiently automate these density operations. And unfortunately, those two goals are often in tension. What do I mean by that? Well, there are a host of language features that we would like to support to help users define their probability distributions. But if we throw them all into one language, the automation task of computing density ratios for inference becomes intractable. And so in practice, today's languages only support subsets of these features, carefully chosen to ensure that the automated densities required for inference, or density ratios, are tractable to compute exactly. Now, this talk is about a new design for a probabilistic programming language that allows us for the first time to support all of these features simultaneously. And you should be suspicious of this claim, because I just told you that if we throw all of these into one language, then the density ratios that we need for inference are intractable to compute exactly. And so the trick that we're playing here is that we're not going to try to compute those density ratios exactly. We're going to settle for stochastic estimates of the density ratios. But we won't just use any stochastic estimates. We'll do it in a way that doesn't compromise on accuracy or soundness. So to achieve that, we had to do a few things. First, we had to rethink the central abstraction at the core of today's probabilistic programming languages, the computational representation of a probability distribution. So in existing systems, distributions, primitive distributions for example, are objects that know how to generate samples and evaluate densities. That works great if the densities you're evaluating are exact, but if you start plugging in approximate versions of these density operations, they start behaving very poorly under composition. And that's because this interface wasn't designed with compositional approximation in mind. So our first step in this work is to redesign this computational interface to support compositional density estimation. So we've come up with a new interface based on estimating densities and density reciprocals. And we've gone back through sort of the standard textbook inference algorithms and rewritten them to rely on this new interface to probability distributions instead of the sample density interface to probability distributions. And crucially, distribution objects that satisfy this new interface compose nicely. And that lets us build a compiler that takes in source programs in a very expressive modeling language and automates the implementation of the stochastic probability interface for the user's programs. Finally, we perform an empirical evaluation based on 6 case studies from the modeling and inference literature. So let me start by talking about this stochastic probability interface. So the user's ultimate goal in probabilistic programming is often to implement some algorithm for probabilistic reasoning, like MCMC. These algorithms are parameterized by one or more probability distributions, and usually the user has some idea of what distributions they want to use. With probabilistic programming systems, users can define those distributions compositionally as programs. Then, when the algorithm requires sampling or density functions, these operations can be automated by special program transformations or interpreters. So to be more concrete, let's take a look at what these programs look like and how densities are typically computed in probabilistic programming systems. So these systems usually come equipped with a collection of primitive distributions, which have known density functions that are easy to compute. For example, a Gaussian distribution or a categorical distribution. These primitives can then be composed into more complex probability distributions. So for example, one way that we can compose them is that we can write programs that interleave samples from these primitive distributions with standard programming constructs like conditionals and loops. And when we do this, we're going to interpret the resulting program as defining a joint distribution over all the primitive random samples that the program makes. So in this case, over all possible assignments to the variables n, z, and x. And these joint distributions, the densities of these big joint distributions can be computed by multiplying the densities of individual primitive distributions that were used to define it. So these joint distributions are easy to compute densities of. They're also often very useful, but sometimes they're not what the user actually wants to express, right? Sometimes the user writes a program like this, and they don't want to think about the distribution over n, z, and x. Instead, they want just the marginal distribution over a final returned variable, say x. In other words, they want to encapsulate these internal variables n and z and treat their program as defining a new univariate primitive. Now, even though these marginal distributions are very useful, their densities are often difficult to compute because we have to sum or integrate over all possible values of these n and z variables that we're marginalizing out. And that's why languages like SPPL that support marginalization as a feature, as a first-class feature, have to restrict other features to ensure that these sums end up being finite and tractable to compute. Another powerful feature for building probability distributions is conditioning a distribution on an observation, like the predicate that z is greater than or equal to 2. But computing conditional probabilities similarly requires sums and integrals, which are again only tractable if other language features are restricted. So how can we possibly support all of these language features at once, if the densities of users' programs are going to involve these intractable sums and integrals over all possible assignments to the program's variables? And the key thing that saves us is that in these algorithms that users want to run, it turns out that it's okay to estimate the density ratios that come up rather than compute them exactly. Intuitively, the overall algorithm is already stochastic, so as long as we add new noise in carefully and don't add too much new noise, the overall algorithm is still going to satisfy the same correctness property that it did before. And so what we've done with the stochastic probability interface is we've come up with a unified specification for density estimation that allows us to implement a wide variety of inference algorithms in this careful, sound way. And the interface consists of two methods. The first is called estimate density, and it takes as input a point x and outputs a positive random weight w. It's probably the first thing that you'd think of when I say that we're going to be stochastically estimating densities. The correctness requirement is just that it's unbiased, meaning that on average, over many samples from this density estimator, you get the true density p of x. And if this were all that we were doing, we wouldn't need a new interface. You could just go into the existing sample and density interface and change out the density with estimated densities. But that wouldn't suffice for implementing the kinds of inference algorithms that we want. And the reason is because, as I mentioned earlier, we often need to compute ratios of probability densities. And if I just get two unbiased estimates of two different numbers and then I divide them, that does not give me an unbiased estimate of the ratio. So dividing introduces bias. We can't just push this division inside of the expectation operator. And so this is what motivates the second method of the interface, simulate with reciprocal weight. And this method takes no arguments. It's sort of our version of sample. And in addition to producing a sample x from the distribution, it also produces a weight w. And the property of w is that it's conditional expectation, or the conditional expectation of 1 over w. So w itself is the reciprocal of an unbiased estimate of 1 over p of x. Okay? And these two methods together form the stochastic probability interface. And for any given distribution, even many distributions that don't have tractable exact densities, there are many valid implementations of this interface, which strike different trade-offs between computational cost and variance. But the payoff, if you have some implementation of this interface, is that a host of Bayesian inference algorithms can all be soundly implemented on top of it. So here I'm showing sort of our versions of some standard textbook inference algorithms, where instead of sample and density, I've highlighted in yellow where we are calling estimate density, and in blue where we're calling simulate with reciprocal weight. So you can implement sound versions of all these algorithms on top of this stochastic probability interface. So that's the interface. It lets us do sound inference without exact densities, and that enables our next contribution, a really expressive probabilistic modeling language which supports automation for inference by compiling programs down to this stochastic probability interface. And our language, is a standard deterministic language augmented with standard probabilistic programming features, but also new constructs for first-class marginalization and conditioning. And the point of our compiler is to take in a program in this language, which our semantics says denotes some probability distribution. And we're going to model our compiler as a program transformation into a target language that produces two programs, one for each of the methods of the stochastic probability interface. And the correctness property that we're going to satisfy is if we look at the target language semantics of those two produced programs, they together implement the stochastic probability interface for the denotation of the original program. So how does this compiler work? Well, primitive distributions with exact densities are handled just like in standard probabilistic programming languages, and joint distributions are still easy. We can multiply together these estimates, and they become estimates of the joint densities. So really, the only key challenge here is how are we going to handle these new features of normalization and marginalization, first-class constructs for those operations inside of the language. Because these features introduce these intractable sums and integrals. And the key idea that we're going to exploit here is that the problem of computing these densities can actually be reduced to a problem of posterior inference. If we see a value x that's returned from this marginal program, the question is, what value of n and z could have been used to produce it? And that posterior inference question is one that probabilistic programming people have been thinking about for decades. We have algorithms that are pretty good at exploring the space of executions of this program in order to find the ones that likely lead to x. And not only do we have algorithms for this, we have DSLs, programmable inference DSLs, that let you sort of express these algorithms as terms inside of the probabilistic programming language. So our solution to this sort of design problem is that every time a user calls normalize or marginal, they're going to annotate that call with a term that says, hey, and here's the Bayesian inference algorithm that you should automate, that the system should automate in order to estimate the marginal or normalized density. So our compiler is going to use the inference algorithm that the user specifies to automate the implementation of the stochastic probability interface. And that means that we're going to use these inference algorithms not just to estimate the marginal density or the normalized density, but also the reciprocal of the marginal or normalized density. And that was non-trivial to get working. We had to implement some new analyses of this inference DSL that automate the construction of the time reversal kernel of an MCMC kernel that the user specifies, for example, or the conditional variant of a user-specified SMC algorithm. All of this machinery works compositionally. So, for example, the algorithm that you specify to perform conditioning can itself rely on a proposal distribution that was built using marginal. And this ability to support this kind of composition rests crucially on our having rethought the computational interface that boxes like these expose to consumers like MH. So that's the language and compiler. And we evaluated our approach by re-implementing the Gen probabilistic programming language to use these new interfaces. And we evaluated it on 6 case studies from the modeling and inference literature. And Bayesian approaches to all these problems have a long history, and GenSP makes it possible to tackle them using probabilistic programming despite intractable densities arising either in the model itself or the sophisticated proposal distributions necessary for accurate inference. So for each of these case studies, we implemented 3 versions of the same algorithm and measured how accuracy changes as we use more computation. In all the plots I'll be showing you, the blue curve is the algorithm that uses our system, GenSP. The orange curve is the same algorithm but hand-coded from scratch in Julia. And the green curve shows a version of the same algorithm but using slow exact density evaluation if possible. With our experiments, we set out to answer 3 questions. First, when exact densities are available but slow, how much does GenSP's estimation speed them up? And we found that GenSP's automated estimators were 1 to 7 orders of magnitude faster than slow exact density implementations that we wrote by hand. Second, how much overhead does GenSP's automation introduce compared to hand-coded versions of the same density estimation-based algorithms? So on micro benchmarks, GenSP introduces about 3x constant factor overhead, but that overhead disappears when we look at integrated benchmarks that measure accuracy versus time over the course of a longer running algorithm. And that's because these estimators are fast enough that the bookkeeping performed by MCMC or SMC accounts for most of the runtime of the algorithm, to the extent that doubling or even tripling the cost of each density query has a negligible effect on the overall runtime. Finally, how does estimating the density affect the convergence of inference relative to an idealized exact density version of the algorithm? And we found that convergence was basically unaffected. So that's illustrated in the plots on the far left here, where the x-axis is no longer time in seconds, but rather iterations of the algorithm. And you can see that the GenSP estimator in blue takes about just as many iterations to converge as the idealized exact density version in green. And that's true even though the, if you look at like the MH acceptance rate, it's gone down a bit because of the noise in the density estimates. And the same story holds for sequential Monte Carlo algorithms. So the key takeaways here are that we've taken the sample density interface for probability distributions and we're proposing a replacement for it that supports better compositional approximation of densities. That allows, and the second key takeaway is that in order to automate that interface for programs compositionally, we need to compositionally apply these posterior inference algorithms that our community has been developing for decades, but newly modified to estimate densities and their reciprocals. And finally, the payoff is fast, accurate inference in an unprecedentedly broad model class. So you can find the implementation on GitHub, and as was mentioned, I'll be looking for academic jobs in 2024, so would love to talk more. Thank you.
Questions?
Hey, that was a great talk. Thanks a lot. So there's this paper I'm sure you've heard of from Tom Rainforth about nested estimators. So what that paper said was essentially that if we, have multiply nested inference, there's a challenge in propagating and doing that correctly because the outer inference will depend on the inner inference and you have to estimate those correctly. I didn't see the solution in this talk, and I'm curious if you could comment briefly on what you did.
Yeah. So there's a slight difference in the setting of Tom Rainforth's nested inference and our nested inference. So for us, so we have these new features, marginal and normalize. Marginal, the semantics, the denotation of a program that uses marginal is the marginal distribution. It's the exact marginal distribution. Our version of normalize has a denotational semantics that depends on the normalization algorithm you're using. So what you get is when I say that I want to normalize this program using MCMC, what that denotes is the 1,000-step marginal of the MCMC chain, which is an approximation to the true normalized distribution. So not only is the semantics itself kind of an approximation, then we're approximating the density of that marginal distribution. So that's one difference. And you might say, and so I think an interesting question to look at is in these models that people like Tom were exploring, where you're modeling agents who are doing inference about other agents. Is it better to model those agents as doing exact inference, or is it better to model those agents as actually also having computational limitations and doing approximate inference? The other thing is that when we say nested inference, because we're working in a language with programmable inference, nested inference does mean models that use inference algorithms inside, but it also means proposals that use inference algorithms inside. And there are fewer challenges in that setting just because where proposals come up in the computations of these ratios.
Cool. Thank you.
Thanks.
Any other questions? So I have one, I was wondering can you actually, because do you handle non-linear functions these actually create much more complex densities? So can you approximate the distribution you can get? The angle I'm coming from is, let's say, in neural networks, we have ReLU activation function. So
yeah, so right, if I understand right, the question was if I'm using big nonlinear functions in my programs like neural nets, can you still get the densities of the outputs?
Yeah.
And there's sort of two cases. One is where the final value that's returned at the end of the program. Well, first of all, the challenge with those kinds of programs comes up with this marginal feature. If I have a variable x and then I run a neural net and then I sample a variable y, the joint density of x and y is still easy to compute. I just have to run the neural net while computing that density. But if I want now the marginal density of the output of the neural net or something like that, that can be really complicated, right? We can't get a marginal density of a GAN, for example. But we can get a marginal density of a VAE. And the difference between a GAN and a VAE is whether the sort of last thing that happens is a random choice, or if the last thing that happens is a deterministic thing. So if you look at how the marginal feature is actually formalized in our system, it requires that the sort of return value, that the final return value at the end of the program was a sample from distributions. So even if you had neural nets in the middle, we can still do that. But if the neural net is literally the last thing that happens and there's no noise after, then we need some way to invert the neural net in order to compute densities, and we can't do that in general.
Okay. Let's thank the speaker again, and then let's welcome the next.